You might not be the only person hearing these words right now. Parallel universes are not just science fiction. They are legitimate scientific theories that some of the most brilliant physicists are investigating seriously. This is the multiverse, a staggering concept where countless versions of reality exist alongside our own. You will discover 25 compelling reasons, rooted in quantum mechanics and cosmic mysteries, that explain why scientists give this radical idea serious credence. What if every choice you have ever made created another world where a different version of you lives out the alternative? How could ancient light from the Big Bang contain bruises from collisions with other cosmic bubbles? By the end, you will understand the powerful evidence that is reshaping our fundamental understanding of reality itself. What single discovery about our universe would most surprise you? The quantum realm operates by a bizarre set of rules, a place where particles can be in two places at once or spin in opposite directions simultaneously. This strange state is known as quantum superposition, famously illustrated by the thought experiment of Schrödinger's cat, a creature sealed in a box that is paradoxically both alive and dead until someone looks inside. For decades, scientists argued this was merely a question of our knowledge, that the cat was one or the other, and we just did not know which. But in the 1950s, a physicist named Hugh Everett proposed a far more radical explanation. He suggested the paradox is not about uncertainty, but about reality itself splitting in two. In one universe, you open the box to find a living cat. In another parallel universe, an identical version of you opens the identical box to find a corpse. The act of observation does not collapse the possibilities. It chooses which branch of reality you will experience. Every single quantum event, from the decay of an atom to the path of an electron, becomes a fork in the road for the cosmos. Picture reality as a cosmic choose your own adventure book. Every time you, or even a single particle, faces a decision, the book does not just let you turn to one page. Instead, the entire story duplicates. One copy continues with your choice to turn left, while a brand new, equally real copy is created where you turned right. This is the many worlds interpretation. It means there is a universe where you took that different job, a universe where you never met your best friend, and even a universe where a single coin you flipped once landed on the other side. The sheer number of these branching timelines is beyond human comprehension, a vast, ever-expanding tapestry of what if. This is not just philosophy, it is a direct mathematical consequence of the quantum equations that have proven so stunningly accurate. If the fundamental laws of physics are true, then this endless branching may be the inevitable architecture of existence. So the next time you are kept awake by a choice you made, wondering about the road not taken, there is a profound and scientifically plausible possibility that another version of you is living that very life, on a branch of reality just out of reach. The branching of reality does not stop at the quantum scale. It extends to the very fabric of the cosmos, born from the theory of cosmic inflation. In the first fleeting moments after the Big Bang, our entire observable universe is thought to have undergone an incredible growth spurt, expanding from smaller than a proton to a vast, macroscopic size in a fraction of a second. This was physicist Alan Guth's revolutionary idea, solving several major puzzles about our universe's structure in one bold stroke. But the most profound implication is that this inflationary process might not have been a one-time event. It may be eternal. Think of a pot of water coming to a rolling boil. Bubbles form, expand, and merge. Now picture the fabric of space-time as that boiling water, a seething, energetic state known as a false vacuum. In this bubbling cosmic soup, regions of space can randomly drop to a lower energy state, like a bubble forming in the pot. When this happens, inflation stops inside that bubble, and a stable universe like our own is born. But outside that bubble, in the vast sea of false vacuum, the frantic expansion continues unabated, endlessly giving birth to new cosmic bubbles. Our entire cosmos, with its hundreds of billions of galaxies, would be just one bubble in an infinite cosmic foam. Each of these bubble universes could be entirely separate, forever out of reach beyond the inflating space between us. Even more mind-bending is the possibility that when a bubble forms, the laws of physics themselves could crystallize differently inside. The strength of gravity, the mass of an electron, the number of spatial dimensions, all of these fundamental constants we take for granted might be mere local bylaws, unique to our particular bubble. In another universe, gravity could be repulsive, or atoms might never have formed. This eternal inflation framework provides a compelling, physics-based mechanism for a multiverse, one where an infinite array of realities, each with its own unique history and physics, are constantly being born. So the next time you look up at the stars, consider that you are not just looking out into space, but also across an unimaginable ocean of other worlds, each a separate bubble in an endless, bubbling cosmic sea. The mathematics that so perfectly describes our reality may be the very thing that demands other realities exist. Physicists are discovering that the fundamental equations, from the quantum rules governing atoms to the relativistic laws shaping galaxies, rarely yield a single, neat answer. Instead, they offer a landscape of possible solutions. Each valid solution to these core equations could represent a universe with its own unique properties. Think of a simple equation like x squared equals 4. It does not have one answer, but two possible solutions, positive 2 and negative 2. The universe may operate on a similar, unimaginably vast principle. Our cosmos, with its specific constants and laws, might just be one answer to a much grander cosmic equation, with all the other solutions being equally valid and physically real somewhere else. This leads to a staggering philosophical idea, often summarized by the phrase, anything that can happen does happen. If a set of physical laws is mathematically consistent and allows for a stable universe to form, then somewhere in the infinite expanse of the multiverse, that universe must exist. There could be a reality where light travels slower, where time runs backwards, or where the concept of color is entirely different. This is not wild speculation, but a direct consequence of taking our most successful mathematical descriptions of nature at their word. The numbers themselves seem to be pointing toward a reality far richer and more diverse than the single universe we can see. If the math allows for it, then somewhere, in the grand scheme of things, it is already real. This perfect cosmic tuning presents a profound mystery. Why are these numbers so precisely set to allow for our existence? The strength of gravity, the mass of a proton, the force that binds atoms together. If any of these constants were altered by even a tiny fraction, the universe would be sterile. A slightly stronger gravitational force, and stars would burn out in millions of years instead of billions, leaving no time for life to evolve. A slightly weaker nuclear force, and hydrogen would never fuse into helium, meaning no stars would ever shine at all. The odds of this perfect balance occurring by pure chance are astronomically small, like rolling a die and having it land on the same specific number 1 trillion times in a row. This is the fine-tuning problem, and it demands an explanation. One compelling answer comes from the multiverse idea. If an infinite number of universes exist, each with randomly set physical constants, then it is no surprise that we find ourselves in one of the very few where the numbers just happen to come out right. In this vast cosmic lottery, most universes are stillborn or barren, but a lucky few, like our own, hit the jackpot. This line of reasoning is tied to the anthropic principle, a philosophical concept that sounds complicated but is really quite simple. The weak anthropic principle just observes that we can only exist in a universe capable of supporting life, so we should not be shocked to see one that is fine-tuned. It is like a puddle wondering why the hole it sits in fits it so perfectly. The strong anthropic principle takes it a step further, suggesting that the universe must have properties that allow life to arise at some point. The multiverse gives these principles a physical home. We are not at the center of a cosmos designed just for us. We are simply the fortunate inhabitants of one habitable bubble in an endless froth of realities. Every atom in your body, every star in the sky, is a testament to a cosmic accident that, somewhere in the multiverse, had to happen. The fine-tuning of our universe finds a possible home in one of the most ambitious theories ever conceived. String theory proposes that the fundamental building blocks of reality are not point-like particles, but unimaginably tiny, vibrating strings. The way each string vibrates determines the properties of the particle it becomes, much like a single violin string can produce different notes. But for this elegant mathematical symphony to work, the theory requires more than the 3 spatial dimensions and 1 time dimension we experience. It demands a total of 10 or 11 dimensions, all curled up into a space so small we cannot perceive them. This is where the concept of a multiverse explodes into an almost ungraspable scale. The specific way these extra dimensions can fold and curl is not unique. Physicists have calculated a truly staggering number of possible configurations. A figure so vast, it is written as a 1 followed by 500 zeros. Each of these 10 to the 500 possible shapes defines a universe with its own unique set of physical laws and constants. In one configuration, the folds might produce a universe where gravity is strong and stars are short-lived. In another, the folds create a cosmos where electromagnetism is too weak for chemistry to ever begin. Our universe, with its life-permitting rules, is just one entry in this cosmic catalog, one specific tune played on the vibrating strings. This is the string theory landscape, a vast terrain of possible realities where every mathematically consistent set of laws exists somewhere. This idea is taken even further by M-theory, a grander framework that unites different versions of string theory. It suggests that our entire 3-dimensional universe could be a membrane, or brain for short, floating within a higher dimensional space called the bulk. Other brains, other entire universes, could be floating right alongside our own in these unseen dimensions, separated by a gap we are fundamentally unable to cross. We might be like pages in a book, each page a separate universe, existing in the same volume but never truly touching. The collisions or interactions of these brains could even have been the trigger for events like our own Big Bang. So the next time you feel the solid ground beneath your feet, remember that the very laws making that solidity possible might be the local result of how unseen dimensions are knotted, with an infinity of other realities existing just a vibration away. Our universe has a specific shape, and we have measured it. Satellites like WMAP and Planck have mapped the faint afterglow of the Big Bang with incredible precision, revealing a startling fact. The geometry of our cosmos is flat. Not flat like a sheet of paper, but flat in the sense that parallel lines will never meet, and the angles of a triangle always add up to 180 degrees. This measurement is not a rough guess. It is exact to within a razor-thin 0.4% margin of error. A flat geometry has a profound implication for the size of reality. It suggests that the universe does not curve back on itself like a sphere, but extends, possibly forever, in every direction. What we call the observable universe, with its hundreds of billions of galaxies, is just our tiny, visible patch within an immeasurably larger, and likely infinite, whole. Now, consider the matter within this infinite space. While there are vast cosmic structures like galaxy clusters, on the very largest scales, matter appears to be distributed roughly uniformly. It is like a cosmic foam where the bubbles are unimaginably large, but the overall density looks the same no matter where you are. Combine an infinite, flat space with a finite number of ways particles can be arranged, and something incredible must happen. In an infinite cosmos, every single possible configuration of matter must repeat. There are only so many ways to arrange a collection of atoms to form a planet, a person, or a historical event. Given an endless expanse, those arrangements are not just possible, they are inevitable. Somewhere in a galaxy identical to our Milky Way, there is an identical Earth. On that Earth, a person identical to you is reading these very words. Another version of you chose a different path this morning, or lives in a world where a single historical event unfolded differently. This is not a quantum split or a separate bubble, but a duplicate born from the sheer, staggering scale of infinity. The light from that other Earth will never reach us, as the space between us is expanding faster than light can travel. But the mathematics of infinity suggest it must be there. You are unique in your local cosmic neighborhood, but in the grand, infinite tapestry of a flat universe, every possible story is being told, not just once, but an infinite number of times. Einstein famously called it spooky action at a distance, a phenomenon so strange it seemed to break the universe's speed limit. Quantum entanglement links two particles in an intimate dance, no matter how far apart they travel. Change the spin of one entangled particle, and its partner instantly responds, as if they share a single existence across the void. This non-locality defies everything we know about space and time, suggesting a hidden layer of connection beneath the fabric of our reality. One radical explanation is that this spooky connection is not a signal traveling through space, but a consequence of the particles sampling different branches of the multiverse. When you measure an entangled particle, you are not forcing its partner to react. Instead, your act of observation places you on a specific branch of reality where the two measurements are correlated. Another version of you, on a parallel branch, sees the opposite correlation, and both outcomes are equally real. This is not a faster-than-light signal, but a synchronization across the vast tree of possibility. Imagine two magical dice, one on Earth and one on a planet in a distant galaxy. You roll yours and get a 6. Instantly, you know the die far across the cosmos also shows a 6. It did not communicate. It was always 6 in this branch of reality the moment you looked. This bizarre interconnectedness is the foundation for quantum teleportation, where the state of a particle is instantaneously transferred to another location. The particle itself does not travel, but the information defining it is shared across the entangled connection, effectively recreating the original in a new place. This process hints that what we perceive as separate locations might be illusory, mere facets of a deeper, unified multiverse. If particles can be linked in a way that transcends space, then perhaps our entire conception of reality as a single, continuous stage is fundamentally incomplete. We are not isolated observers in a vast emptiness, but active participants in a cosmic network where every choice, every measurement, weaves us deeper into an infinite tapestry of parallel worlds. This observation problem strikes at the very heart of reality. Why does a quantum particle, existing in a blur of multiple possibilities, suddenly pick a single, definite state the moment we measure it? The traditional explanation, known as the Copenhagen interpretation, presents a strange and almost mystical answer. It proposes that the very act of conscious observation forces the particle's wave function to collapse from a spectrum of probabilities into one concrete outcome. Before you look, an electron is everywhere it could be. The instant you detect it, it snaps into one specific location, as if your awareness commands it to choose. This idea places human consciousness in a bizarrely powerful cosmic role, a notion that makes many physicists deeply uncomfortable. It raises more questions than it answers. What qualifies as an observer? Does a cat count? A camera? A single-celled organism? The line is hopelessly blurred, creating a paradox where the rules of the universe seem to depend on who is watching. The many worlds interpretation sweeps this entire messy problem away with a breathtakingly simple solution. There is no collapse. When you measure that electron, you are not forcing it to choose. Instead, the entire universe splits. In one branch, you find the electron in one location and record that result. In a newly formed parallel branch, an identical version of you finds the electron in a different spot and records that. Both outcomes are equally real. The measurement problem vanishes because every single possible outcome is actualized somewhere. The particle does not have to pick a state. It simply manifests all of its possible states across the sprawling multiverse. What feels like a random, probabilistic outcome in our world is simply our limited perspective on an infinitely branching reality. This is not just a philosophical preference. It is a matter of elegance and parsimony. Why invent a special, unexplained process of wave function collapse that hinges on vague definitions of consciousness, when the core quantum equations already describe a reality that naturally and continuously splits? The math points toward many worlds, offering a cleaner, more complete picture of how the quantum realm operates. So the next time you make a simple observation, remember that you are not collapsing possibilities. You are simply stepping onto one path in an endless garden of forking ways, while other versions of you step onto all the others, each one exploring a different, fully real outcome of that single fleeting moment. Deep within the heart of a black hole, where gravity becomes infinite and spacetime curves to a breaking point, our understanding of physics simply ends. This point of no return is the singularity, a one-dimensional tear in the fabric of reality where the known laws of nature cease to apply. But what if this is not an ending at all? Certain solutions to Einstein's own equations for general relativity hint at a breathtaking possibility. The tunnel through spacetime predicted by these equations, the wormhole, might not just connect two distant points in our universe. It could bridge the gap between entirely separate cosmic realms. On the other end of this cosmic tunnel, the mathematics points to the existence of a white hole. If a black hole is a one-way door where nothing, not even light, can escape, a white hole would be its exact opposite. It would be a point in another universe from which matter and energy can only pour outward, a cosmic fountain of creation that nothing can ever enter. This suggests a staggering cycle. The matter and energy swallowed by a black hole in our cosmos could be violently reborn, spewing out as a new Big Bang in a separate baby universe. This is not just science fiction. It is a legitimate, though highly speculative, consequence of the very equations that define gravity. Physicist Lee Smolin took this idea and forged it into a radical theory of cosmic evolution, which he called cosmological natural selection. He proposed that every single black hole in our universe is the seed for a new universe inside it. And just as in biological evolution, there could be a process of inheritance with slight mutation. The fundamental constants of physics in that daughter universe might be randomly tweaked compared to the parent. Most of these new universes would be stillborn, with laws too unstable to form stars or atoms. But a rare few, with constants tuned just right for producing an abundance of black holes, would be the most successful. They would win the cosmic competition by spawning the most offspring universes. Over countless generations, this process would naturally select for universes, like our own, that are exceptionally good at making black holes. Our cosmos, then, might not be a lonely accident. It could be one branch on a vast, growing tree of universes, each born from the corpse of a star in a reality that came before. We may be living inside a universe that itself was born from a black hole in a grandparent cosmos, part of an endless, self-replicating chain of existence. A single, self-aware brain could spontaneously form from the chaos of empty space. This bizarre idea is the Boltzmann brain paradox, a thought experiment that emerges directly from the fundamental laws of thermodynamics. These laws tell us that systems tend toward disorder, a state called high entropy, yet they also allow for the possibility of random fluctuations, where particles can momentarily arrange themselves into orderly structures, even incredibly complex ones. In a vast, eternal, and empty universe, the random assembly of a fully formed, conscious brain, complete with false memories of a past that never happened, is statistically more probable than the formation of an entire, ordered cosmos like our own. The odds of every particle in the universe arranging itself into galaxies, stars, planets, and people are astronomically low. It is far easier for a fluctuation to create just one isolated brain floating in the void than to create the entire history we remember. So why do we find ourselves in this staggeringly improbable, structured reality, and not as lonely, disembodied minds adrift in nothingness? The multiverse offers a powerful resolution. If countless universes exist with all possible configurations of matter, then of course we find ourselves in one of the rare, orderly ones capable of supporting sustained, complex life. In the overwhelming majority of universes, conditions are chaotic and barren, with perhaps only a fleeting Boltzmann brain popping into existence before dissolving back into chaos. But we could not possibly experience that. Consciousness can only arise and persist in a stable, low-entropy environment like our own. The paradox vanishes because we are not a statistical fluke in an empty void. We are inhabitants of a specific, finely tuned universe within an infinite ensemble. A universe where the long, structured history we perceive is not an illusion, but the very real foundation of our existence. Our ordered reality is not a miracle. It is a selection effect in a cosmos of limitless variety. The map of the universe's first light holds a ghostly signature of its violent birth. This cosmic microwave background, a faint afterglow from the Big Bang, is not perfectly smooth. It is dotted with tiny variations in temperature, the seeds from which all galaxies would eventually grow. But some features on this ancient map are deeply puzzling. One of the most famous is a vast cold spot, a region of space far chillier than our models can easily explain. It is a cosmic anomaly, a place where the universe seems to have a mysterious bruise. One compelling and thrilling possibility is that this bruise was caused by a collision with another universe. During the period of eternal inflation, when our cosmic bubble was first forming, it may have bumped against a neighboring bubble universe. Such a titanic impact would have transferred immense energy, but not in the way you might think. The collision would not have created a hotspot. Instead, it would have drained energy from the region, leaving a lasting cold imprint on the fabric of our newborn cosmos, a permanent scar from a close encounter with another reality. This is not the only anomaly. Scientists have also detected strange alignments in the CMB's temperature patterns, large-scale asymmetries that suggest a preferred direction in space, almost as if our universe was tugged and shaped by an external force. Could these also be the fingerprints of a multiverse, the gravitational pull from other cosmic bubbles just beyond the veil of our perception? These are not just abstract ideas. They are physical predictions that can be tested against the data. Researchers are now scouring the most detailed maps of the cosmic microwave background, searching for the specific patterns, the telltale rings or disc-like shapes that would be the smoking gun of a bubble collision. We are looking for the dents and scratches on the surface of our own reality, evidence that we are not alone in the greater cosmos. Finding them would be a discovery of unparalleled magnitude, our first direct glimpse into the multiverse. The answers to the deepest questions about existence might not lie in the distant future, but are already written in the oldest light we can see, waiting for us to decipher its ancient, cryptic message. Gravity feels like the dominant force in our daily lives, holding planets in orbit and our feet firmly on the ground. Yet in the subatomic world, it is almost laughably feeble. The electromagnetic force that binds atoms together is a trillion times stronger. This baffling mismatch is known as the hierarchy problem, and it is one of the most profound puzzles in all of physics. Why is the force of gravity so incredibly weak compared to the other fundamental forces? The standard model of particle physics offers no answer, leaving scientists to wonder if our understanding of gravity itself is fundamentally incomplete. One elegant solution emerges from the idea of extra dimensions. Perhaps gravity is not weaker, it is simply more spread out. Picture our three-dimensional universe as a vast, impossibly thin sheet, a membrane floating within a higher dimensional space. The other forces, like electromagnetism, are trapped on this membrane, confined to our three dimensions. Gravity, however, is different. It can leak. It can seep out into the extra dimensions, diluting its strength from our perspective. What we perceive as a weak gravitational pull might be the faint echo of a truly powerful force that is mostly operating in realms we cannot see. This concept, known as the brain world scenario, provides a natural explanation for gravity's feebleness without inventing new particles or altering fundamental constants. It suggests we are living in a cosmic neighborhood where gravity is shared with other universes just a whisper away. The most exciting part is that this is not just theoretical speculation. It could be tested. The Large Hadron Collider, the world's most powerful particle smasher, is on the hunt for evidence. When protons collide at nearly the speed of light, they release tremendous energy. In some collisions, scientists predict they might see a telltale signature of these hidden dimensions, a small but consistent amount of energy that simply vanishes from our detectors. Where does it go? This missing energy could be gravitational waves or even entire particles radiating away into the extra dimensions, carrying their energy with them out of our perceptual reach. A confirmed detection would be a revolution.
our first experimental proof that our universe is just one layer in a much richer, multidimensional reality. The solution to one of physics' greatest embarrassments may not lie in making our universe more complex, but in realizing it is part of something infinitely larger, a multiverse where gravity's true power is simply hidden in plain sight. The vacuum of space is not truly empty. According to quantum field theory, it should be a seething, boiling cauldron of energy, with particles and antiparticles constantly flickering in and out of existence. This vacuum energy should exert a powerful gravitational repulsion, a force so immense that it would have torn our universe apart in the first split second of its existence, preventing anything from atoms to galaxies from ever forming. The math is clear and terrifying. The energy density of this quantum vacuum should be a number with 120 zeros after it. But when we measure the actual force driving the universe's expansion, the cosmological constant, we find a value that is almost zero. It is not just a little off, it is off by a factor of 10 to the 120th power. This is the greatest mismatch between theory and observation in the entire history of science. A discrepancy so vast it is like predicting an ocean and finding a single, solitary drop of water. How can our most successful theory of particles be so catastrophically wrong about the energy of nothingness? The multiverse offers an elegant, if humbling, solution. If an infinite number of universes exist, each with a randomly chosen value for the cosmological constant, then the vast majority will have values as enormous as the theory predicts. Those universes would blow themselves to pieces in a violent flash, or collapse back on themselves instantly, never forming a single star. They are cosmic dead ends. But in an infinite array, every possible number will appear somewhere, including numbers very close to zero. We exist in one of those incredibly rare, incredibly precious bubbles where the vacuum energy is almost perfectly balanced, allowing for a long, stable cosmic evolution where galaxies can coalesce and life can ponder the mystery. This is the anthropic principle in its most powerful form. We are not here despite the strange numbers, we are here because of them. The cosmological constant problem vanishes when we stop asking why our universe is so uniquely fine-tuned, and instead realize we are simply the lucky inhabitants of the one in a Google universe where the numbers allowed us to be. The bizarre power of a quantum computer does not come from being faster, but from being everywhere at once. While a classical computer bit is a simple 1 or a 0, a quantum bit or qubit is a superposition of both states simultaneously. This allows a quantum computer to explore a staggering number of possible answers to a problem all at the same time. When you run a calculation on a few hundred qubits, the machine is not just testing one potential solution. It is effectively testing trillions of pathways in parallel. This phenomenon is known as quantum parallelism, and it is the source of these machines' mind-bending potential. But how does it actually work? One compelling explanation, favored by pioneers like David Deutsch at Oxford, is that the quantum computer is not just simulating multiple answers. It is physically leveraging the computational power of parallel universes. In this view, each possible state of the qubit exists in a separate branch of the multiverse. When the quantum computer enters its superposition state, it synchronizes its operations across these countless realities. Different versions of the computer then work on different parts of the problem simultaneously. The final act of reading the result is what brings you the answer from the branch where the calculation succeeded. It is as if you enlisted an infinite number of identical teams, each working in their own isolated world, to solve a puzzle, and you simply receive the correct solution from the team that found it. This is not just a poetic metaphor, It is a serious interpretation of what the equations describe. The sheer processing power appears to come from a resource far greater than our single universe, a distributed network of reality itself. So when a quantum computer finally cracks a code that would take a conventional machine the age of the universe to solve, it may be offering us more than just an answer. It could be providing our first functional evidence that we are tapping into the vast, collaborative power of the multiverse. Time itself may be the ultimate illusion. Our everyday experience tells us that time flows from a fixed past into an uncertain future, a relentless river carrying us forward. Yet when we look at the fundamental laws of physics, this flow vanishes. The equations of general relativity, which govern the cosmos, and the equations of quantum mechanics, which rule the tiny, are deeply at odds about the nature of time. In Einstein's theory, time is woven into a four-dimensional fabric of spacetime, but it is just another dimension, not something that moves. In the quantum world, time is a mysterious, external parameter that nobody fully understands. The quest to unite these two pillars into a single theory of quantum gravity has led to a startling possibility. Our perception of a flowing present may be a local artifact, a trick of the mind that only makes sense within our particular branch of the multiverse. Some of the most promising approaches to quantum gravity, like the Wheeler-DeWitt equation, are fundamentally timeless. They describe the entire universe, or even the entire multiverse, in one static, frozen picture. In this view, the past, present, and future all exist simultaneously, laid out like scenes in a vast, unchanging film reel. This is the block universe theory, and it suggests that your birth, you listening to this now, and every future moment are all equally real and permanent. They do not come into being, they just are. So why do we feel time passing? The multiverse may provide the answer. What we experience as the flow of time could be our conscious journey along a single, winding path through the infinite, timeless landscape of the multiverse. Every quantum decision, every choice, moves us from one static block to another. The feeling of a moving now is our awareness traversing this eternal structure. This has a profound and perhaps unsettling implication for free will. If all moments are fixed, are our choices an illusion? Not necessarily. In the branching multiverse, every possible decision you could make is realized in some branch. Your sense of choosing is the reality of you navigating this tree of possibility. Your life is not a predetermined track, but an exploration of a landscape where every path is real. You are not a puppet on a string, but a traveler constantly deciding which of the infinite, already existing versions of yourself you will become. The river of time does not flow, it branches. And we are the current, flowing through every possible moment, living all the lives we were ever destined to choose. Far beyond the reach of our most powerful telescopes, a mysterious current pulls at the fabric of our cosmos. Astronomers have observed something deeply strange, a phenomenon they call dark flow. Hundreds of galaxy clusters are not moving randomly, they are streaming in a coherent direction, as if being drawn by a colossal gravitational presence that lies entirely outside our observable universe. This is not the gentle drift of cosmic expansion. It is a purposeful flow towards something we cannot see. The sheer scale of this motion is staggering, suggesting the source of this pull must be unimaginably vast, a structure so massive it defies our current understanding of cosmology. What could possibly exert such a powerful gravitational tug from beyond the edge of everything we know? One of the most thrilling explanations is that we are feeling the influence of another universe. Just as the moon's gravity creates tides in our oceans, a neighboring cosmic bubble, a separate universe with its own mass and structure, could be pulling on the matter in our own. This dark flow would be the first detectable evidence of a reality beyond our cosmic horizon, a ghostly hand reaching from another dimension to guide the motion of our galaxies. Not all scientists are convinced, of course. The measurement itself is incredibly difficult, and some argue it could be a statistical fluke or an artifact of how we map the cosmic microwave background. The debate continues, a quiet war fought with data and equations. Yet the possibility remains, a siren call from the void. Future missions, like the European Space Agency's Euclid telescope, are designed to map the cosmos in unprecedented detail. They will scrutinize this dark flow, searching for the subtle fingerprints of its origin. If this cosmic streaming is confirmed, it would fundamentally rewrite our place in the cosmos. We are not an island universe, but one piece in a grander archipelago of realities, forever connected by the invisible, relentless force of gravity. Our own reality might be the most advanced form of virtual reality. The simulation hypothesis suggests that everything we see and feel could be an intricate computation running on a computer built by a civilization vastly more advanced than our own. This is not just a plot from a science fiction movie, but a serious philosophical argument proposed by thinkers like Nick Bostrom. His simulation argument presents a striking trichotomy. At least one of these three propositions must be true. First, almost all civilizations like ours go extinct before developing the necessary technology. Second, advanced civilizations have no interest in running simulations of their ancestors. Or third, we are almost certainly living in a simulation. If even a small fraction of advanced civilizations choose to run ancestor simulations, the number of simulated minds would dwarf the number of biological ones. Statistically, you are far more likely to be one of those simulated beings. This technological scenario creates a multiverse of a different kind. A single advanced civilization could spawn countless simulated worlds, each with its own slightly tweaked physical laws or historical timelines, all running as programs on some unfathomable hardware. Our universe, with its strange quantum rules, might offer clues that we are inside such a construct. The discrete, pixelated nature of reality at the smallest scales, the way quantum particles only resolve into definite states when observed, could be seen as processing optimizations. It is the universe conserving computational resources, only rendering the fine details when someone is looking. This connects the natural multiverse we have been exploring to an artificial one. The bubble universes of eternal inflation and the branching worlds of quantum mechanics could be the underlying physics engine, while a simulated multiverse would be the software running on top of it. The philosophical implications are dizzying. If our cosmos is a simulation, then the beings who created it might themselves be inside a simulation, in an infinite regress of realities within realities. Whether the multiverse is a fundamental feature of nature or the ultimate technological artifact, the conclusion is similarly humbling. We are part of something impossibly vast, a single thread in a tapestry of existence whose true scope and nature we are only beginning to glimpse. The very fabric of our reality might be a single swirl in an infinite fractal. Chaotic inflation theory proposes that the multiverse is not just a collection of separate bubbles, but a living, breathing structure, constantly growing and replicating in an eternal, chaotic dance. It begins with that same primordial energy field, the false vacuum, but this time we focus on its inherent quantum chaos. At these unimaginably small scales, the energy field is never perfectly smooth. It is a turbulent sea of random fluctuations, with tiny regions constantly jittering up and down in energy. Normally, these quantum jitters are fleeting, appearing and vanishing in an instant. But during the frantic expansion of inflation, something extraordinary happens. A tiny region that randomly fluctuates to a higher energy state can be stretched faster than it can decay. In a cosmic blink, this minuscule fluctuation is magnified to a macroscopic size, becoming a new pocket of inflating space. This pocket then becomes a new universe, budding off from its parent and beginning its own eternal journey of expansion and replication. Our entire cosmos, with all its galaxies and stars, could be the child of one such quantum tremor, a random shiver in the fabric of a parent universe that was itself born from a shiver in another. This process has no beginning and no end. It is a self-sustaining reaction, an eternal chain of cosmic reproduction where each new universe becomes a potential parent to countless others. The resulting structure is not just infinite, it is fractal. Zoom in on one region of the multiverse, and you find a branching tree of universes. Zoom out, and that entire tree is just one branch on a larger tree, and so on forever. The large-scale structure of all existence mirrors the intricate, repeating patterns of a snowflake or a fern, but on a canvas of literally cosmic proportions. Those same quantum fluctuations that gave birth to our universe also left their permanent mark on it. As inflation stretched those tiny energy differences to cosmic scales, they became the seeds for all future structure. The slightly denser regions in the early universe, imprinted by that ancient quantum noise, eventually collapsed under gravity to form the first galaxies, stars, and planets. The vast cosmic web we see today, with its glittering galaxies and dark, empty voids, is the grown-up version of a microscopic quantum froth. This means the pattern of the entire observable universe, every place you could ever go, was determined by random quantum jitters during the first fraction of a second of existence. You and everything you know are the result of a chaotic fluctuation that was frozen into the cosmos and stretched to an immense scale. We are not just living in one universe among many, we are living proof of an eternal, chaotic, and breathtakingly beautiful process of creation that has been, and always will be, generating new realities across the endless expanse of eternity. Our universe runs on a specific, reliable set of physical laws. But why these particular laws? Physics has always sought a single, elegant theory of everything, one that would uniquely predict every constant and force we observe. Yet that quest hits a profound wall, a meta-law problem. Why is the mathematical bedrock of reality this specific set of rules and not another? The multiverse provides a radical shift in perspective. Instead of searching for a unique set of fundamental laws, we might be living in a cosmos where the laws of physics are more like local environmental conditions. Think of our universe as a single planet in a vast cosmos. On Earth, the climate allows for liquid water and life. On Mars, the conditions are frozen and barren. The laws of physics could be the same way, not universal and absolute, but regional features that vary from one cosmic domain to the next. In one region, the strength of gravity might be set to one value, allowing for stable galaxies. In a neighboring bubble universe, that constant could be different, resulting in a cosmos that collapses instantly or flies apart too fast for stars to form. This transforms our search for a final theory. The ultimate goal is no longer to find the one set of laws, because there may not be just one. Instead, the theory of everything would be a meta-law, a rule that describes the entire landscape of possible physics and explains why some sets of laws are more common than others. It would be the statistical map of the multiverse, showing the distribution of all possible cosmic environments. We find ourselves in one that is habitable not because the laws are special, but because we could not exist in the vast, uninhabitable majority. This does not make the laws of physics arbitrary. It simply places them in a much grander context. The deep structure of reality is not defined by a single equation, but by a spectrum of possibilities, and our existence is a single data point within that infinite variation. The answer to why our laws are the way they are may not be an elegant derivation, but a simple statement of location. We live in the neighborhood where the rules allow for our story to be told. A single, terrifying thought experiment pushes the logic of quantum branching to its absolute limit. It is called quantum suicide, and it suggests a bizarre form of immortality. Imagine a device is built, connected to a quantum trigger like the decay of a single radioactive atom. Each second, the device checks the atom. If the atom has decayed, a gun fires, killing you instantly. If it has not decayed, the gun does nothing, and you hear a safe click. Now, according to the standard view of a single reality, your odds are a 50-50 chance with each passing second. Sooner or later, the atom will decay and you will die. But the many worlds interpretation tells a different story. In this view, the universe splits with every quantum measurement. In one branch, the atom decays, the gun fires, and that version of you dies. But in the very same moment, another branch is created where the atom did not decay. The gun clicks harmlessly, and you remain alive. This process repeats second after second. From your first-person perspective, you only ever experience the branches where you survive. You will hear an endless series of safe clicks forever. You become a quantum immortal, incapable of experiencing your own death, because any fatal outcome simply creates a parallel reality where it did not happen. This logic extends beyond a macabre laboratory setup. It implies that for any potentially fatal event in your life, from a car crash to a falling piano, there is always at least one branch of the multiverse where you miraculously survive. From your conscious point of view, you will always find yourself on that branch, no matter how improbable the escape might seem. The philosophical implications are deeply unsettling. It suggests your continued existence is not a matter of luck, but a mathematical certainty within the infinite sprawl of reality. Most physicists firmly reject this as a misinterpretation, arguing that it confuses your subjective experience with objective reality. They point out that the you who survives is not the same continuous consciousness as the you who died, but a new, separate entity on a different branch. The version of you reading this now is simply one thread in a vast tapestry, and that thread will inevitably be cut. The thought experiment is not a recipe for immortality, but a stark illustration of how our intuition about self and survival breaks down completely in the many worlds framework. It forces us to ask what we even mean by I. Are you a single, continuous consciousness, or are you simply one of countless copies, each believing themselves to be the original? Quantum suicide does not offer eternal life, but it does highlight the truly strange and counterintuitive consequences of taking the multiverse seriously, revealing a cosmos where identity itself is a fragmented and fleeting concept. Look at the night sky in any direction, and you will find the universe looks remarkably the same. The temperature of deep space, the types of galaxies, the fundamental laws, they all appear uniform no matter where we point our telescopes. This cosmic consistency presents a profound puzzle known as the horizon problem. The issue is one of timing and connection. The oldest light we can see, the cosmic microwave background, shows that regions of the universe billions of light years apart have almost identical temperatures and properties. Yet, according to the standard Big Bang model, these regions were never close enough to exchange heat or information. They were born beyond each other's cosmic horizons, forever out of touch. It is as if you walked into a vast, crowded room where millions of strangers, who have never met or communicated, are all wearing the exact same outfit, down to the smallest detail. How could such perfect coordination occur without any contact? The leading solution is cosmic inflation. This theory proposes that in the first fleeting fraction of a second, our entire observable universe was compressed into a tiny subatomic volume where every point was in intimate contact. This region was then stretched to a colossal size faster than the speed of light, smoothing out all irregularities and locking in that initial uniformity. The distant regions we see today were once neighbors, able to share a common temperature before being violently ripped apart by inflation's incredible expansion. This solves the horizon problem for our single cosmos, but eternal inflation takes this elegant solution and projects it onto a multiverse scale. In the eternal chaotic froth of the false vacuum, new bubble universes are constantly budding off from a shared parent region. While these bubbles become permanently causally disconnected, forever isolated by inflating space, they inherit their fundamental physical parameters from that common origin point. Different bubble universes could share similar laws and properties not by chance, but because they were born from the same quantum fluctuation in the inflationary field. They are cosmic siblings, sharing a family resemblance despite living in separate, unreachable homes. This provides a natural explanation for why we might see certain patterns or constants repeating across the multiverse. The large-scale homogeneity we observe is not a mysterious coincidence, but a frozen relic from a time when everything we know was connected, a final, fading echo from the moment of our cosmic birth. The most intimate mystery is the one happening inside your own skull. Consciousness, the raw feeling of what it is like to be you, presents the hard problem. Why do electrochemical signals in the brain create a subjective, inner experience of the color red or the taste of chocolate? Science can describe the neural correlates, but it cannot explain the leap from physical process to personal awareness. Some physicists and neuroscientists propose a radical solution, that consciousness is not a classical phenomenon at all, but a quantum one. They suggest the brain might be a sophisticated quantum computer, and our sense of self emerges from processes that touch the multiverse. The renowned physicist Roger Penrose, together with anesthesiologist Stuart Hameroff, developed a theory called orchestrated objective reduction. It proposes that the seat of consciousness lies deep within our neurons, in structures called microtubules. These tiny protein scaffolds are not just structural elements. They could be where quantum computations take place. Penrose suggests that these quantum states in the microtubules remain in superposition, processing information in multiple states at once, until they reach a certain threshold of complexity. At that precise moment, the theory states that the tiny space-time curvature around these superposed particles, a quantum gravity effect, causes them to collapse to a single state. But this is not the random collapse of traditional quantum theory. This collapse is a moment of self-selection, an event where a specific outcome is chosen from the quantum possibilities. And here is the profound connection to the multiverse. In the many worlds interpretation, that collapse does not actually happen. Instead, the universe branches. So how does Penrose's theory fit? It suggests that each conscious moment, each flicker of thought and sensation, is a process where our brain's quantum system briefly interacts with the underlying geometry of reality, sampling different branches of the multiverse before settling onto one specific path. Your stream of consciousness, the continuous flow of your inner world, could be a sequence of these selections, a journey through the tree of possible realities experienced from a single, subjective point of view. This would mean that every conscious choice you make, every new idea that forms, is not just a neural calculation, but a quantum gravitational event that anchors you to one thread in the infinite tapestry. While this theory remains highly controversial and is not widely accepted, it represents a breathtaking attempt to bridge the gap between the mind and the cosmos. It proposes that we are not just passive observers of a quantum world, but that our very awareness is woven from its fundamental fabric, a dance between the microscopic structure of our brains and the unimaginably vast architecture of all that is. Our universe is built almost entirely from matter, a fact so ordinary it seems to demand no explanation. But this is one of the deepest enigmas in all of physics. According to our best theories, the Big Bang should have created equal amounts of matter and antimatter. For every particle of matter born, an identical twin of antimatter should have emerged. These two are perfect opposites, destined to annihilate each other in a flash of pure energy upon contact. If the cosmos had begun in perfect symmetry, all of those particle pairs should have mutually destroyed one another, leaving behind a vast, empty sea of radiation with no atoms, no stars, and no us. Yet here we are in a world made of matter. Almost all the antimatter has simply vanished. This is the missing antimatter problem, and its solution requires a fundamental asymmetry in the laws of nature, a set of conditions that favored the survival of matter over antimatter by the tiniest of margins. Physicists call this process baryogenesis. It requires that the early universe violated three key principles just for an instant. There had to be a process that treated matter and antimatter differently, a departure from thermal equilibrium to break the symmetry, and a mechanism that prevented the antimatter from simply reforming. The standard model of particle physics does contain the seeds of such an asymmetry, but when we run the numbers, the effect is far too weak. It can only account for a surplus of about 1 particle of matter for every 10 billion particle-antiparticle pairs that annihilate it. That 1 in 10 billion difference is all that remains of everything we see. It is the ultimate close call, a razor-thin margin that allowed our entire cosmic structure to exist. So why is the asymmetry so perfectly, delicately tuned to allow for a rich, complex universe? The multiverse offers a humbling perspective. Perhaps the fundamental rules that govern baryogenesis are not fixed, but variable. In the endless landscape of bubble universes, the outcome of that primordial battle between matter and antimatter is decided by a random roll of the cosmic dice. In the vast majority of universes, the symmetry is perfect. Matter and antimatter completely annihilate, leaving behind a cold, dark, and empty void. In other realities, the asymmetry might swing the other way, creating a cosmos dominated by antimatter. An antimatter universe would be virtually indistinguishable from our own to an outside observer. Antistars would shine with the same light, antiplanets would orbit them, and in theory, anti-life could evolve. But if a matter universe and an antimatter universe ever made contact, the result would be the most spectacular release of energy imaginable, a total conversion into light. We simply live in one of the rare, fortunate bubbles where the numbers fell in favor of matter, by just enough to build galaxies and give us a story to tell. The mystery of our existence is not why the laws of physics are perfect, but why they are just barely good enough. in a cosmos where almost every other possibility leads to nothing at all. The search for other realities is not confined to telescopes and abstract math. It is happening deep underground in the world's most powerful machine. The Large Hadron Collider smashes protons together at nearly the speed of light, recreating conditions that have not existed since the first moments of the Big Bang. Scientists meticulously sift through the debris of these microscopic fireballs, searching for any particle that behaves unexpectedly. One of the most tantalizing hints of a multiverse would be the discovery of missing energy. In countless collisions, physicists have observed a small but consistent anomaly where energy seems to vanish from their detectors without a trace. Where does it go? One compelling explanation is that this energy is not disappearing, it is escaping. It could be carried away by particles that are not bound to our three-dimensional universe, radiating out into the hidden dimensions predicted by string theory. Think of it like a game of billiards played on a table with hidden holes. You see two balls collide with a certain force, but the resulting motion does not add up. Some of the energy is missing because a ball, invisible to you, has fallen through a pocket into another room. In the collider, that missing energy could be a gravitational particle, a graviton, slipping out of our brain and into the bulk, the higher dimensional space that may contain other universes. Another profound quest at the LHC is for supersymmetry, a theory that proposes every known particle has a heavier super partner. If discovered, supersymmetry would provide a natural home for the extra dimensions required by string theory, strongly supporting the idea of a brain multiverse. While these super partners have remained elusive, their potential discovery would revolutionize our understanding of reality's architecture. Every anomalous particle decay, every unexplained signature, is a potential clue. We are not just probing the fundamental building blocks of matter, we are testing the very boundaries of our cosmos, searching for the faint, telltale cracks that might reveal we are not alone in the greater multiverse. This ancient yearning for cosmic completeness may be the final and most profound reason to entertain the multiverse. For millennia, philosophers have argued that a truly perfect and full reality would leave no possibility unfulfilled. Plato hinted at a world of perfect forms, of which our own is but a shadow. Centuries later, the brilliant thinker Gottfried Wilhelm Leibniz proposed his principle of plenitude, stating that the universe created by a perfect God must be as rich and full as it can possibly be. It must contain every single thing that can possibly exist, leaving no potential unrealized. Why would a boundless creation be limited to just one version of reality? This is not about a deity, but about a logical and aesthetic ideal of maximal richness. For most of history, this was a beautiful but abstract dream, a thought experiment with no grounding in physical law. Today, our most advanced theories of physics are giving this ancient idea a startling mathematical form. The landscape of string theory, with its 10 to the 500 possible vacuum states, is a physical embodiment of plenitude. The infinite expanse of a flat universe, where every possible arrangement of matter must repeat, is another. The quantum many worlds interpretation, where every choice branches into a new reality, is perhaps the ultimate expression of this principle. The cosmos is not just a single sparse story. It is an exhaustive library containing every book that could ever be written, every tale that could ever be told. Every universe with stronger gravity, every reality where dinosaurs still roam, every world where you made that one different choice, all of them are out there, not as ghosts of what might have been, but as concrete physical realities. This provides a deep and satisfying completeness to existence. No mathematical possibility is wasted. No potential goes unrealized. The multiverse, in all its staggering variety, fulfills a fundamental human desire to see the cosmos as a place of infinite potential, where nothing that can happen is ever truly lost. We are not living in a lonely, singular reality, but as participants in a totality so vast and complete that it encompasses all of existence in every possible form. The sheer weight of these ideas, converging from the edges of quantum theory and the vast scales of cosmology, builds a compelling case for realities beyond our own. It is not a single, fragile argument, but a chorus of evidence from different corners of physics. The bizarre certainty of quantum mechanics suggests a cosmos that branches with every decision. The elegant solution of cosmic inflation paints a picture of an eternally bubbling vacuum, spawning countless cosmic islands. The inexplicable fine-tuning of our universe finds a natural home in an infinite landscape where every possible set of physical laws must appear. Even the ghostly imprint of dark flow and the mysterious cold spot in the ancient sky hint that our cosmos may not be perfectly isolated. Together, these threads weave a tapestry of a reality far grander and more interconnected than we ever dreamed. While a direct photograph of another universe remains beyond our grasp, the theoretical foundation is robust, spanning from the mathematics of the infinitesimally small to the geometry of the impossibly large. This shifts our place in the cosmos from the center of a single, special creation to inhabitants of one humble neighborhood in an endless metropolis of existence. Your life, with all its unique joys and sorrows, is being lived in countless other ways across this infinite expanse. This is not a demotion, but a liberation, an invitation to see our reality as one note in a boundless cosmic symphony. The greatest mystery is no longer whether other universes exist, but what their existence reveals about the fundamental nature of everything. Stay curious, for the next great discovery could be just around the corner, or perhaps in the universe right next door. We would love to hear which of these parallel universe theories captures your imagination the most. Share your thoughts in the comments